let's move on to the next presentation. I think, okay, you might have to stop sharing the screen.
Hello, morning.
Hey, Jiajun. Wait a minute.
Yeah,
I think
hello.
Kayan has not stopped sharing the screen. Yeah. Now we have your name.
Okay.
Okay, so the
So,
next presentation is coming from Jiajun Ye from Ryzen. Jiajun is a senior product manager at Ryzen Energy, and he is going to talk about HyperIon Pro, their new module. So title of his presentation is HyperIon Pro, Redefining HJT Mass Production Towards 740 plus watts. Jiajun,
thank
the
you.
floor is yours.
Thank you for the introduction. Yeah. And good morning, everyone. I'm Jiajun Ye, product manager from Ryzen Energy, and happy to be here and introducing a little bit our new advancement in technology and our mass production status. So to start, I would like briefly introducing our companies. Ryzen is a company which was founded in 1986, which is around 20 years ago, and we started our PV manufacturing from 2002, which already have 22 years histories. And so far we have expanded our production capacity to 48 gigawatt, including all the technology like PERC, TOPCon heterojunction. And cumulative shipment of our model has been distributed in the world, more than 60 countries and regions, in total 95 gigawatt production capacity. And also, we are one of the pioneer of heterojunction R&D and mass production. We started our heterojunction production and R&D from 2018, 7 years ago. And just after years of R&D, we launched our first heterojunction products in 2019, around 6 years ago. And by then, we are using a small wafer, which is 156. And we know by 2022, we are entering the new wafer area, which we utilizing M10 and G12 solid cells. So we redeveloped our heterojunction model based on 210 cells and launched our whole new heterojunction products in 2022 called HyperIon. And with this year's, and also at the year after, we also built some new facility for the heterojunction production solely, because we know that the production line for heterojunction one is not compatible to the old ones. We invest a lot on this. And by end of 2023, we already established 15 gigawatt production capacity for heterojunction. And in this year, we extended another 6 gigawatt. So in total, we already have 21 gigawatt production capacity for heterojunction ones. And also in the meantime, we never stop R&D and introduce a lot of new technology to boost our efficiency and also as well to maintain the reliability. And here next we'll also into some also Ryzen is also a fully integrated companies. We have production in all scales, starting from the polysilicon manufacturing and ingot wafer. So we have very fully control our supply chains. And here are some production bases we have distributed in the world. In moment we have in total 8 production bases, 1 in Malaysia and 7 in China. And among these 8 production bases, 2 are for heterojunction production. As we can see here, as mentioned before, we have 21 gigawatt production capacity for heterojunction. And also, we also have 90 gigawatt production capacity for heterojunction cells as well. So next, we'll talk about the technology we've been introduced to the heterojunction. As we know that heterojunction is a technology which was introduced very long time ago, around 1974. That's almost 50 years ago. But why it takes so long to bring for the whole industry to bring this technology into the mass production, not like TOPCon introducing in 2013, but already in mass production in 2022, 8 years, because we believe to provide good commercial and sustainable products, there are 3 key factors we have to achieve. First one would be production cost, second one would be efficiency, and third one reliability. So in the past, the main challenge for the heterojunction technology to be a commercial product is that the high cost, because compared to other technology, heterojunction emitter is of lower like conductivity. So to improve the conductivity of the whole cell, we have to apply the silver paster, which we know that silver is very expensive. And if we introduce this by then with silver paster, the cost of this product will be very high. That's why in the past years, we've been always searching the good like alternative to replace the silver paster. And just in recent years, with our commitment and also some third parties work like efforts, we are already reaching some new advancement, which is silver paste, like coated copper paste with slow silver consumption, and also the other options as copper paste, copper plating. But now mainstream in the market with still like low silver pasters. And by introducing this technology, we could reduce large silver consumption lower than OC so far, lower than 6 microgram per watt peak, which is even lower than TOPCon and and the top PERC as well. To further reduce our cost, lower than 44.4 euro RMB cent, lower than other technologies. And we are commercially ready for this mass production. And then we also try to introduce a lot of new technology, like which Hosong introduced like zero bus technology to lower the shadings, and also some technology was very hot in the market, like low temperature processings, and also non-welding technology, and also low wafer low wafer thickness, and also the low solar cell thickness. And to summarize, we'll also see that we, as I mentioned before, we are pioneers in this heterojunction field. We've been starting in the mass production and R&D since 7 years ago. That's why make us leading in this new technology. Like we are the first one who introducing the zero busbar solar cells, and the first one to reduce the solar cell thickness for heterojunction from 150 to 90 micrometers. And we first want to reduce the silver consumption lower than 6 microgram per watt peak. And we are also introducing our own patent, low temperature and stress-free interconnection technology called HyperLink for the interconnection between the cells to avoid some welding technology, thermal damage caused by the conventional welding technologies. Yeah. And this is some advancement or achievement we have made in the past years. And just in this half year, we also introduced some, this years, we have introduced some new technology to further reboost our efficiency and power output, which can be higher in compared to other products and technologies. And there are 3 of main technology we'll be introducing. The first one we like to introduce is we call high mobility targeted material. As I mentioned before, for heterojunction technology, we have slightly lower conductivity in the emitter, which is amorphous silicon layers on the surface we have here in the front side and back side. And so solely with this emitter, we are not able to achieve the high efficiency. So we have to introduce a new actual solutions for this one, which we have the TCO layer on the surface, and offering both conductivity and also light transmittance, also working as anti-reflection layers. And to deposit or to create this layer on the surface, a field deposition process called target material splitting will be adopted, which is the target material will be bombed by high-speed ion beams, and causing these atoms from spotted target material to spotted on deposit on the substrate, which is a solar cell surface we have here on this microcrystal silicons. And later on, then we're forming this thin layer, yeah, as from outermost layer for both front side and back side. And industrial, and as I mentioned, this layer offers both features conductivity and also transparency as well, light transmittance as well. So if we trying to improve the efficiency from this layer or based on this layer, there's mainstream in three direction. First one will be lower the resistivities of the surface, and also the second way is to higher the transmittance of this layer, and the last one will be the low temperature growth capability of this layer. And in the market, it's mainstream in the industry, the mainstream of this the improvement of this, like, for this layer will be to lower the resistivities. And this formula demonstrates the resistivity of this layer. So we can see the main way to reduce it is to improve the concentration, carrier concentration of the layer, and also to increase the carrier mobility of this layer, TCO layers. And from this two way, if we increase solely, so carrier concentration, we not only lower the resistivity, but also will be higher the light absorption of this TCO layer, which means the light from the sunshine will be absorbed by this TCO layer, but not be utilized from the solar cell itself. Thus, it will be reduced efficiency, but not improve directly the efficiency. And if we increase the carrier mobility, then we can only improve the resistivities. So to reach an optimal level for the cell efficiency improvement, we have to balancing these two parameters simultaneously. So, but after our study, we found proper material and composition for this target material to reaching an optimal level of this for this sputtering target material and also deposition. And thus we have improved carrier mobility around 29.11% for the solid TCO layers. And by increasing this carrier mobility while maintaining good composition of the carrier concentration, we improve the efficiency around 0.02% for single cells. Yeah. And the next technology we introduce is the stencil scrimping technologies, and which we already know about a lot in the past, because we know on the surface of the cells to collect the current, we're not only using the ammeter, but we're also using the green lines on the surface, the bus bar or fingers, to collect the current and transfer into the main circuits. And in conventionally, we are using the scrimping technology, which is demonstrated here. The ink, or we see the paste will be placed on the mesh, and using the squeeze, pressing some giving some pressure and allowing the paste to penetrate and through the mesh opening to deposit on the surface of the solar cell surface. And in the past, we are using the conventional ones, which we have using the made of warmed stainless steels, and we have mesh here in between the openings. So the ink penetration will be, or see the paste penetration will be not 100%. But now we are introducing the stencil scrimping technology, which we are seeing here. So we have this is a kind of knotless printing technology. So the ink of the paster can go through, go past the opening directly, but without any blocking. So we will have higher paste and ink transmittance, and also to lower a little bit the paste consumptions as well. And here's some picture showing the paste we have to created with this technology. As you can see, the thickness of the fingers, obviously the green lines, are much thinner compared to previous one, reduced from 32 to 24. So we have less shading by introducing this technology. Yeah. And also we have more open active area for receiving the sunshine to utilize the efficiencies. And also it's mentioned by introducing the film, this stencil scrimping technology, the green line we are painting will be more precise controlled, which means the aspect ratio of the green line will be more will be higher compared to previous time, improved from 20% to almost 50%, and to improve a lot of the fill factor for the whole cells. And the last technologies, which also already being mentioned by Dr. Ding, and this UVID light convert, also awesome, is a kind of light conversion films. Because recently year, when we're introducing the high efficiency heterojunction solar cell, a main topic is higher UVID degradation, and which is mainly caused by the UV light penetration in the solar cell, causing the silicon nitride bond was being broken down, and to lower the passivation effect for the whole cells. And in the past, we are using the UV cutoff film, which can like, stop like UV light to penetrate in the solar cell. But in this way, we will lost a part of like UV energy which can be utilized by the sunshine. So the new technology is introducing the light conversion field, which by using the Stokes shift to switching UV light into the visible blue light, and then convert this energy to the light to the solar cell surface. Thus, we can not only lower the UV impact, but also improve the efficiency. And here's some comparison between the conventional cutoff film to the conversion film. And in the left picture, we can see in different wavelengths, ultraviolet part, we're seeing that when the wavelengths of the light are higher than like 350s, the difference between the cutoff line and the UV conversion line will be further widened, which means the main like degradation we still can cause by this part, even we introduce the cutoff film. So conversion film can perform better in this has better like a cutoff ability compared to solely cutoff films. And also we done some UV test, which is UV 240 test. You can see after this test, the UV light transmittance for the UV light conversion film still remain unchanged, but for cutoff film, it will this feature will be slightly decreased. The more UV light will be surpassing this film and onto the solar cell surface, cause degradation. That's why for the solar cell scale of the model scale, the UV degradation for the heterojunction one with UV conversion field will be much lower, which better compared to the model with like cutoff film. And also he mentioned, which also mentioned, Horsten has mentioned that we can also not only improve the reliability and lower degradation, we also improve a lot, power output for the solar cells, around 10 megawatt, 10 to 15 megawatt for single cell. That's why when we're introducing all this new technology, we're launching this half year like new hydrogen product called Hyperion Pro, and offering mass production up to 730 watt in mass production. And this is something already happening in our mass production line, and we are start offering this product to the market Q1 next year. We're already receiving a few orders from this one. And with the efficiency of the model will be further improved quarterly. So we suppose by end of next year, we can offer in the market 740 watt models. And here's some key specification for this model. This is standard model size, and we are offering the best temperature coefficient is -0.24% per degrees, which offering the a superior performance under high temperatures. And we're also offering the highest bifacial factor among all the technologies, or about 85% for the model and the cells. And also we're offering the lowest degradation in the market, which 0.3% annually. Which means after 30 years, we still can have 90.3% power retention rate. And we are offering industrial standard N-type warranty, 15 years for the product and 30 years performance warranties. And our model has been undergo all kinds of stringent tests to verify its performance, or Saltime state, ammonia test, Dasan test to maintain to secure our performance in all kinds of application scenarios with severe conditions because of climate change. And at last, we'll show some outlooks for our companies. As I mentioned so far, we are heading to 740 watt mass production next year, and we are also trying have a team to study the combination of BC technical structure with heterojunction. And we suppose we will have some new products or some launching in 2026 based on heterojunction, BC structures. And also we know that a tandem cell will be the main trend in the next generation technology, and this is also our main focus. Our team are also working on this, trying to combine heterojunction structure with perovskite. And we believe that in 2-3 years later, we can launch our tandem cell technology based on heterojunction bottom cells. And by then we can have launching, we can offer 850 watt plus models for our clients in after 2027 round. So yeah, I will close here. I think time's up. Thank you.
Thank you, Jiajun. So one question I have
Yes.
is, you mentioned stencil printing, but stencil
Yeah.
printing is not really new though. So this was
Yes.
evaluated several times in the past. So what really changed now that stencil printing started looking attractive for solar cell makers like you?
We see, because this is more like stencil technique, as I mentioned before, that we are still using the silver paste, coated pasters. To further reduce the silver consumption, we need to lower the paste consumption. So the stencil will be better to compatible with like heterojunction technology as well. With conventional technologies or stencil technologies, a lot of improvement can be made because, as I showed before, the micro pictures, the aspect ratio we can further improve to higher levels, that we can reduce first in the thickness of the finger lines or green lines, and also to improve the aspect ratio of the green line we are printing with stencil technology. That's to improve the efficiency in this way. So there's still a space to further improve in these technologies.
And so, if you're using stencils, obviously they are more expensive, right? So the savings in the silver and the gain in efficiency, can they compensate the additional costs? You compared to your previous costs per watt, is it able to compensate these additional costs in the overall gains?
Yes, you're also missing one part, the lifespan. The lifespan of the stencil mesh is also can be longer used compared to screen printing. So all counted together, I would see the higher cost can be compensated for the heterojunction technology.
Okay, thank you. So I still have one more question, but probably I will put it in the chat window. So let me go ahead with the session and move on to the next presentation. And probably there are also a few questions on the chat. So please try to answer these questions along with mine.
Yeah, thank you.